All right, guys. So we've been playing a little bit with this simulation regarding earthquakes and plate boundaries and talking about this stuff in the classroom. I want to get into a little bit of an introduction to what earthquakes are all about. I'm starting here just because this is what we've been looking at, where these earthquakes occur. And we're going to look at how we can actually pinpoint the location of these earthquakes as we progress through this lesson. But let's just start with the basics for now and just talk about what earthquakes do. I'm going to start with basically some pictures. So, this is the earthquake after the San Andreas fault actually shifted about 3 meters back in 1904 after a really, really big earthquake in San Francisco. You can see earthquakes along the San Andreas fault line here that have shifted the ground, and you can actually see the result of that movement side to side as those plates slide past each other. You can see it in this valley that's been shifted over a little bit. You can see it in this orchard. So there's visible evidence of earthquakes that have occurred in the past that end up giving you results like this over time. Here's a really interesting one where you have a vertical shift of the land. This is a track from a high school that got totally destroyed as a result of it. But you can see how much the land can shift just in one simple earthquake. So an earthquake occurs as you have a whole lot of stress building up on either side of a fault line. A fault line is where you have a crack in the Earth's crust. And as those plates slide past each other, they build up a whole lot of tension over time. And that stress will build, and you'll have deformation of the ground below the surface. And that stress gets really, really, really high. It's like you're overwhelmed with a whole bunch of homework, and then something adds to your stress level and you just can't take it anymore. And when that happens, that stress is overwhelming for in this case, the rock. And you just get to the point of you can't take it anymore, and it ruptures and it breaks. And that is the actual earthquake. When it gives way, all that stress is released. It's like snapping a rubber band. All of that energy is then released. And speaking of a rubber band, we actually call earthquakes are very similar to that idea. It's called the elastic rebound theory, where you're building up stress on both sides of a fault. And as that stress builds and builds and bends the rock, eventually that stress level gets to a point where it can't take it anymore, and it releases all that energy. And that energy released in all directions is called an earthquake. So let me just show you a quick simulation of that. I'll play this slow. So if you look at this, you can see there's a block that's being pulled along a kind of a gritty surface. And as he pulls that rubber band, it stretches out, energy is building up, and it releases. And then you're pulling it back even more. Energy is stored until it can't take it anymore, and it finally goes. Okay, so that's exactly what's happening with plates as they slide past each other. Eventually, they give way, and that's your earthquake. Okay, so earthquakes are caused by that sudden release of energy. And that's what it says right here. Stress and strain. Stress is the building up of pressure over time. They can bend and deform, and then finally the strain is the release of that, and that results in a sudden movement of the Earth's crust that releases all of that energy. So an earthquake is going to occur along a fault line, okay, anywhere along a fault line. And it's really impossible to really predict exactly where that stress is going to be released from, but it's like a breaking point in a rubber band. If you stretch a rubber band out, eventually it's going to snap. Where it's going to snap is going to be the weakest point, and that's what we call the focus of an earthquake. The focus is the point below the Earth's surface where it slips and breaks. Okay, so that's the focus point down below the ground. Now, you've probably heard of the term epicenter. The epicenter is the point directly above the focus. So if you follow that on up to the top here, the epicenter is on the surface directly above the focus of the earthquake. So the epicenter is important because that's typically where you would have the most damage if you had human beings living in this area. That's where you would experience the highest amount of damage and shaking due to the earthquake being very close to that. So the focus is below the ground. The epicenter is on the surface directly above that. So note the difference between those two words. Okay? Now, obviously, we've kind of already talked about this. The hazards for earthquakes vary across the globe. but the highest risk of having an earthquake would be along a major plate boundary, as you can see here in California, the San Andreas fault line. There are other fault lines located in other regions, but most of the earthquakes, like we talked about, are occurring along plate boundaries. You can see Alaska has got a nice convergent boundary there that we've looked at. Okay, this is a global look at that, which again, it's the same idea that we've been looking at in the classroom, that most earthquake hazards are along plate boundaries. Now, we measure earthquakes with an instrument called a seismograph. A seismograph measures any type of ground vibration, obviously including earthquakes, but also any other types of ground vibrations. So if you have like a really, really heavy duty big truck that's passing by that kind of rumbles the ground, it'll pick up those tiny little vibrations on the seismograph. Seismographs are really, really finely tuned and pick up tiny little vibrations. Now, a seismogram is the record of that earthquake, which we analyze and look at different waves that we're going to talk about in a second. But the seismograph is the instrument that's below the ground, and the seismogram is the thing that we're reading. And it kind of looks like this. There's something buried below the ground in the bedrock, and it can move. You can have different types of these seismographs that move in different directions that indicate different motion, whether it's up or down, north or south, or east or west. So you have all these different vibration motions. And then that's recorded onto this rotating paper drum here. And this pen wiggles back and forth. And you've probably seen that before. Now, obviously, lots of wiggling means lots of ground vibration, which is probably an indication of an earthquake. And like I said, it's not necessarily limited to that. And sometimes you can have an earthquake caused by human beings. And this happened about 10 years ago now during a Seahawks game. The Seahawks are well known for their fans and their noise level. Obviously not this year so much in the COVID environment. But in 2011, Marshawn Lynch scored a touchdown, and it caused an earthquake that was not necessarily a real earthquake, but it caused vibrations of the seismograph station, which was right down the street from the Seahawks stadium. So you can see the actual record of that, and when they analyzed this, and when he scored the touchdown, and when the replay happened and they replayed it on the big screen, they all started cheering and jumping down again. So it caused an earthquake, and it happened again in 2014 as well. I'll show you a video of that right here.
Crowd silent now, as opposed to when the Saints have the ball. Oh, look at this run! What a run! Marshawn Lynch still on his feet. Has blockers now. He's dancing his way for the touchdown.
Okay, so seismic waves are released from an earthquake. There's a lot of energy that's released during an earthquake, and these waves are going to extend outward in 360 degrees around the focus of that earthquake, just like as if you dropped a drop of water into a very still pond or into a bucket. You'd see all these waves that extend outward from the center. And the leading wave, the one that's in front here, is the one that is the first to leave and the first to arrive on the other side. And so you have different types of waves based upon when they travel, how they travel through the ground. Okay, so these are the two major types of seismic waves that are created by an earthquake. They're called seismic waves. And the first type are called primary waves, or P waves for short. And that's what I'm going to be calling them from now on. So P waves travel fastest. They vibrate back and forth in the direction of travel, which I'm going to show you in a second. They travel very similar to sound waves. P waves are interesting because, well, they're called primary because they travel really fast. They're the first to arrive, hence the name primary. So they travel really fast, and they travel through any type of material, whether it's solids or liquids or even through gases. P waves can travel through the air technically. So P waves will travel straight through the Earth and reach the other side. Okay, so P waves are the fast ones. They arrive first at a seismograph station. They're the first ones to be detected by a seismograph. S waves are known as secondary waves, and they travel slower, hence the name. They're secondary. They come in second place, and they vibrate in a direction which is perpendicular to the direction of travel, or also known as shearing or transverse waves that go up and down and vibrate up and down. And I'll show you a clip of that in a second. S waves can only travel through solids, and that's important. That's something that we'll talk about a little bit later on when we're analyzing the interior of the Earth. we can tell that there's liquids in the center of the Earth, or in the outer core, I should say, because S waves don't travel all the way through to the other side. So again, P waves are first, secondary waves, S waves are second. And then we also have other types of waves that we're going to talk about with ground vibrations that are called surface waves. So P wave motion is a compressional motion. It moves in this direction, back and forth. It wiggles back and forth. And I'll show you a slinky example of that in slow-mo right here. S-wave motion is a shearing motion, a transverse up and down or side to side motion. And you can see this point going up and down in this diagram here. And I'll show you a quick slinky example of that right here. Okay, now on a seismogram, which is the record of the earthquake, we will see nothing. There's no vibrations. And then finally, maybe an earthquake happens sometime before this, and the P wave finally arrives at the seismograph station, and it's detected. There's a little quick wiggle of that P wave arriving. And then sometime later, the second place wave, the S wave, comes along and wiggles the seismograph station. And then maybe after that, if you're close to the earthquake, you might have these surface waves which jump way up and down, which wiggle the entire ground, and you would feel that motion with those surface waves. So that's the typical record of a seismogram, with P first and then S wave afterwards sometime later. The gap between these two waves is a really important thing that we're going to be looking at with your reference table. That's called the lag time. How much time elapses between here and here is really important. It will tell us how far away the earthquake actually occurred. Okay, so we're going to look at some of the information that we can deduce from this. Not only can we tell how far away it happened, we can also tell how strong the earthquake was, the magnitude of the earthquake as well. So this is something that we'll be analyzing in the classroom, and we're going to do something in the hallway where we actually generate something like this. Okay, so we have a P wave, a P wave, and a P wave at 3 different stations that are 3 different distances away. And then the S wave happens afterwards, and it happens afterwards. And you'll notice that the lag time, the time between them, gets greater and greater the farther away it goes. And we'll model that in the classroom. Okay? Now, I want to just show you one more simulation which shows an example of an earthquake and how these P waves and S waves and other waves travel through the Earth and across the surface of the Earth and how they're detected. Okay? So I'll show that right here. So this is a simulation of an earthquake that occurred off the coast of Japan back in 2011. We can do different earthquakes with this simulator, and maybe I'll do that in the classroom. But as you can see here, the actual location, the epicenter of that earthquake was right here where this white dot is located, right off the coast of Japan, which is not visible in this picture. And what I'm going to do is I'm going to hit play, and what you're going to see is a whole bunch of waves that are generated by that earthquake in all directions. The red wave here is representing the P wave, okay, and the blue, the light blue there, is the surface wave, or sorry, the secondary wave, sorry. The yellow are surface waves, okay, that travel across the surface of the Earth. All right, so you're going to see this red line. Don't worry about the PP and the SS wave, but just notice that leading wave here, the P wave, is traveling fastest. It's getting across the globe fastest. It's going all the way across. It's going to be reaching this station over here. And it's going to get across to the other side over to the United States over there and be detected even on the other side of the world. Okay, so these P waves are traveling across. The S wave is going to come in afterwards. Okay, now what you'll notice over here is actually the indications of all those waves arriving at different stations. And you'll notice this is kind of going down. The P wave arrived, and then the S wave arrived. And the P wave arrived, and then the S wave arrived. Okay. And you can see, even at these stations that are over here, the P wave is arriving, or it did arrive, but the S wave never got there. That's kind of interesting. Why would that be? Well, maybe it hasn't gotten there yet. Okay. And then, oh, there it is. It popped up. The S wave finally got to that station. So there's some big time gap here. And obviously, these stations that are on the other side of the globe here are much farther away from Japan. So it takes longer for the S wave to arrive there. There's a bigger lag time there. The other thing I'd like you to notice is that these P waves do travel through the Earth. I'm going to stop that. I'm going to replay it. So watch what happens as they go through the Earth. The P waves and the S waves will travel straight through the center of the Earth. Now you'll notice when that light blue wave, this S wave here, reaches the outer core, it's actually going to get blocked. The P wave goes through just fine. It might have some reflection and refraction bouncing there. But the S wave, it's right here, is going to get blocked because that is a liquid, and S waves do not travel through. They get blocked there. As you can see, they get deflected off. Okay, so there's a lot going on in this example. I'm going to put the link for this if you want to play with this. There's other earthquakes that you can do. There's earthquakes from all across the globe here that happened in different times in history. It's kind of fun to play around with. Neat little simulator there. Okay, now if you have any questions about any of this earthquake stuff, let me know. But that's just a basic introduction to the waves that are generated by an earthquake, as well as what an earthquake does. Okay, and we'll talk more about this as we go on.